Okay, now we have finished up the chapter 7, which is the kinetics, successfully, and now we are entering into the very good, very powerful, very useful chapter, which is the acid-base equilibria. Okay, in which we will learn what are acid, what are base, what are the acid-base equilibria, and what are the acid-base dissociation constant, etc. We will learn in this chapter. Okay, let's go. So now, in this first video, we will study the definitions of the acid: Arrhenius, Bronsted-Lowry acid base, and strong and weak acids, strong and weak base. We will learn about that. What is the Arrhenius acid? What is the Bronsted-Lowry acid? And like that. Okay. So acid, you means the acid, right? You have seen the acids; those are pretty much corrosive substances, right? They react with bases. So lots of things, right? So lots of things we know about the acid. So, but the people know, the humankind know the acid and bases for a long time. They react also together also a long time. But what are the acid and what are the base? That the first time given the definition by the Arrhenius in 1884. Okay, Arrhenius acid base definition is basically it depends upon the activity of those acid base. Acid and base substances with water, and this Arrhenius acid-base definition is the earliest definition actually of the acid. However, it has lots of weakness. It cannot cover all of these acids and base. So later on, Bronsted-Lowry comes, and then finally Lewis comes. Right, Lewis acid-base definition comes. But this is the starting. That's why let's go to the Arrhenius acid-base. What the Arrhenius? So acid is a substance. Now let's see that if you see here. What is acid? Acid is a substance with H in its formula. It should have H, hydrogen is in its formula. Dissociate to yield H plus when dissolved in water. In the aqueous medium, if some substance give the hydronium ion, that is the acid according to the Arrhenius. Okay. So it means that, for example, this is the acid. Let's say this is acid. This will be acid because it has hydrogen present in this formula. Not only that, it should give you H plus ion, okay, and A minus ion, the hydrogen ion when it dissolves in water. Okay, so but generally, more precisely, if we write that if Ha is the acid, if it has an acid here, yes, it has acid. And if you react to that with water, so if we react to that with water, then that will produce hydronium ion. This H plus H2O makes one ion, that is said to be H3O plus ion aqueous, and A minus. Actually, H3O plus ion is similar to the H plus ion. What that is? So Ha gives the H plus, right? And that H plus, but there is water is abundant, right? H2O. So what happens is, so HOH, right? So this is, and there is another H also here. So this kind of structure, but this overall this is positively charged. So this kind of the ion is said to be hydronium, but this is basically H plus ion, hydrogen ion. Okay. Hydrogen ion in water is said to be hydronium ion. It reacts with water and it makes the one temporarily the complex, and that is H plus, H3O plus. So look at that. Now the base is, now that's the acid, okay, which has H in the formula in front. For example, Ha, for example, HCl, H2SO4. See, it is actually what HSO4. That's why hydrogen is here. HNO3. See, H is there. HBr, HI. Okay. H3PO4. Say, let's say that. HClO. Right. They all have hydrogen, right? So they dissociate in water and give the hydrogen. They all are acids. So these are the Arrhenius acids. So Arrhenius base, a base is a substance that has OH minus in formula, hydroxide in the formula, and dissociate to yield the OH minus sign in water. For example, let's say MOH is a formula. Let's say it has a OH minus, right? If you add with water, it will give you M plus aqueous plus OH minus aqueous. These are the basics. Okay, these are the basics. बोला जाए मुझे बोला जाए ना बोला जाए मने यार वीडियो बनवणार आहे क्या बोला जाए दा अब ये सब होने दे यार. Okay, that's the Arrhenius acid base. Okay, so acid hydration, we see that it is an exothermic reaction. That's why in conclusion we just be careful when you mix water and the acid. Okay, so this is for just the caution. Now let's go further the Arrhenius acid base. So when HCl, for example, dissolve in water, it reacts with water, okay, and it gives the hydronium ion. We already discussed about that. Now let us use the curved arrow, which is also said to be the arrow pushing, to show that change in position of the electron pair during this reaction. The first arrow shows the formation of OH bond. The second arrow shows the breaking of HCl bond. Okay, what actually I am saying is, let's see. Okay, let's react any hydrochloric acid or any acid with the water. Okay, so HCl. So let me go here. Okay, HCl, right? HCl, and we are adding that with the H2O. Let's write down this in the form of the Lewis structure. H, showing the lone pair. Now let me show the lone pair here. Plus H and Cl, right? Cl has 1, 2, 3, 4, 5, 6 lone pairs. Okay. So what happens is, so this is the chlorine is electronegative, right? It pulls the electron. So look at that. One bond means, remember, one bond means 2 electron. Okay, always. If you remember the Lewis structure, one bond means 2 electron. Always. One electron from hydrogen, other electron from chlorine. So in the covalent bond, so one bond means 2 electron. One electron from this hydrogen, other from chlorine. That's why 2 electrons. So what happens is, if they react together, if the water come close to the hydrogen, then what happens is this electron pushes to this side, this goes to the chlorine, and if that electron goes to the chlorine, hydrogen don't have any electron, then these 2 electrons, listen, there are 2 electrons, out of these 2 electrons, 1 electron becomes shared. So 1 electron will go to the hydrogen. That's why you have 1 electron, other electron. These 2 electrons makes the bond, and it gives you the new structure, that is oxygen, 1 lone pair, hydrogen, and there is a bond hydrogen. Okay, and these bond have 2 electrons, and 1 electron is this here, other here, other here, other here, and these two, let me change that color of these 2 electrons. Okay, so that is, for example, let's say pink may be better. Okay, these pink electron is here. Okay, these are actually these 2 pink electrons. Okay, so that is structure. Plus chlorine has, now chlorine has 1, 2, 3 lone pairs, right? 6 electrons. That's why now 1 electrons added from here, so it have these many electrons. 1, 2, 3, 1 pair, 2 pair, 3 pair, 4 pair, all 8 electrons. 1 pair, 2 pair, 3 pair, 4 pairs, right? But this is the chlorine minus. Chlorine minus has 18 electrons, right? That's why this is chlorine minus. So this happens. This arrow pushing is just the arrow is where the electrons are going. where the electrons are going, that's the arrow, and from where the electrons are the originating, that is the bottom. Okay, that the head of the arrow is where the electrons are going, tail of the arrow, and where the electrons are originating. So then we use the arrow pushing, this arrow pushing structure, arrow pushing method to show the electrons coming and going for this structure. So Arrhenius acid base. So before that, let's think about the sodium chloride. Okay, if the sodium chloride is an ionic compound, right? That ionic compound, if you put that in water, if you dissolve in water, sodium, the water molecules surround the sodium. We have discussed this many times. And the chlorine also surrounded by different water molecules. Look at that, sodium plus, and water is, the oxygen is pointed toward this. In case of the chlorine, hydrogens are pointed toward the chlorine because chlorine is minus. That happens in case of the ionic compound dissolved in the water. For example, sodium, if you dissolve sodium in water, this happens. But sodium hydroxide, in case of the base, in case of the acid, we have seen that, the arrow pushing previously, right? So, but in case of the base, what happens is, look at that here. So this is sodium, right? Sodium surrounded, this is the chlorine surrounded by the water molecules, and let's say aluminum plus 3 surrounded by these water molecules, 1, 2, 3, 4, 5, 6 water molecules, cobalt surrounded by 1, 2, 3, 4, 5, 6 molecules, right? These all are ionic compounds. But if you add base on the water, then what is happening is, so it is also surrounded, but little bit it go further, see? So sodium is surrounded by 1, 2, 3, 4, 5, 6 water molecules, but one water molecule add with the OH and it makes you this complex. Okay, sodium is here, so one water molecule is here, oxygen, hydrogen, one, another water, another water. So let me give a different color for it. Okay, guys. So then it may be better to understand. Okay. So let me flip for water. Okay. So oxygen, hydrogen, oxygen, hydrogen, oxygen, hydrogen. These are water molecules. Okay. Oxygen, hydrogen, 1, 2, 3, 4. And oxygen, hydrogen. Okay. So see, 1, 2, 3, 4, 5, 6. There it needs the 6. Okay. Yeah, some case you can find out the model 5 model also, but this is 6 hydrogen, 6 water molecule. Okay. So any one of the water molecule, for example, let's say this is, okay, see that this is, there has oxygen and hydrogen. This complex is mixed. Okay, this complex is mixed if the OH minus sign is added, and overall then this is minus sign. So that happens if you add the base. Okay, so not all base initially contain hydroxide ion. Some bases produce OH minus ion by reacting with water. For example, the ammonia, sodium hydroxide already have sodium hydroxide. See, sodium hydroxide has hydroxide, and it gives you sodium plus OH minus when you dissolve in water. But NH3, this is also base, but it don't have any OH, but it is base. How? If you add that with water, it makes you NH4 plus OH minus. That's why this ammonia is base. Okay, because it gives you the OH minus ion. And if something gives you OH minus ion in water, that is base. That's why ammonia is base. So that is about the Arrhenius. So let me discuss about the takeaway for today. Arrhenius acid base. Acid is that gives you hydronium ion when dissolved in water, and it has H in formula. That is the Arrhenius acid. Base that gives you OH minus when dissolved in water, and that contains formula OH minus OH in the formula. For example, HCl is the acid, it has the hydrogen and it will give you hydronium ion, H2SO4. okay, HNO3, right, and this SBr, they all are the originous acid. And the bases, for example, NaOH, CaOH whole twice, these all are and the originous bases. So now let's think about the strength. So acid strength doesn't mean the pH, okay? pH can be any. Generally, if strong acid, yes, we can say that, but otherwise pH can define the strength, but the perfectly list the definition of the strength is if acid 100% dissociates dissociated in water and form H3O plus ion, then this is strong acid. 100% dissociate means, so for example, you have 100 molecule you put in water, all 100 molecule will give you H3O plus, all 100 molecule will give you, for example, Ha, then H3O plus A minus. That happens all of 100 molecules. 100% dissociation, that is strong, or very high dissociation sometimes, okay? So, and similarly, strong base, one that reacts completely with water to form OH minus. 100% dissociation of the base, that is a strong base. 100% dissociation of the acid, that is a strong base. Now here are some examples. Let's 6 most important strong acids. HCl, everything is H. You see that? HCl, HBr, Hi, HNO3, H2SO4 and HClO4. They are strong acids. Okay. Strong base, lithium hydroxide, sodium hydroxide, potassium hydroxide, barium hydroxide, calcium hydroxide. These all hydroxides, right? They are the strong bases. Okay. So those are examples. So what are the strong acids that can get 100% dissociation? Those are the strong acid and strong base. If the base 100% dissociate, that's the strong base. If the acid 100% dissociate in water, that is the strong acid. So again, further, let's discuss about the strength again. Weak acid. What is weak acid and now strong? We know that. So what is weak acid? That don't 100% dissociate. That is weak acid. That 100% dissociate, that base which don't 100% dissociate, only partially dissociate, that is a weak base. For example, the ammonia, NH3, that is a weak base because it dissociates, it produces OH minus ion, H3O plus, sorry, H2O, it gives you NH4 plus OH minus, right? This not the 100%, this is the weak, this one, okay? So for example, the weak acids, all the organic acids are weak acid. For example, acetic acid, CH3COOH, right? And CH3COOH, yes. And propionic acid, methanoic acid, these all are what? These all are what? These all are the weak acids. Okay. The strong acid we have already see the 6 list, and the strong acid, all the organic acids are strong acids. H3PO4, for example. Okay. These are inorganic acids are some also strong. The weak acids. So the weak acids are that has carbon. Okay. Basically. So HCOOH, Cl3COOH, okay, Cl3CH2COOH, they all are the weak acids, and they don't 100% dissociate. And the weak acid and weak base has potential to maintain the equilibrium in the aqueous medium. Okay, they have potential of equilibrium, and they have the potential of the Le Chatelier principle. So also we have, that's why we use the weak acid and weak acid to make the buffer solutions also. That's the reason, and we will discuss that in later. So now let's further go to the strength of the acid and its conjugate base. Acid and its conjugate base. For example, Ha is the acid, A minus is the conjugate base. HCl is the acid, Cl minus is the conjugate base, because H plus Cl minus, right? HCl means, if the HCl means, if for example, if you put HCl in water, so you will get H3O plus Cl minus, right? So this is acid and its conjugate base is minus. If something is acid here plus here, If something is minus here, that is the conjugate base. Okay. So if the strong acids, so it's a H plus and its a conjugate base is weak. Always, if the base acid is strong, its a conjugate base is weak. For example, HCl is strong. You see in the list, right? It's a strong. It's a weak. These are the weaks. They are negligible. They are very, very weak. Okay. So HCl is the strongest acid. It's a conjugate base is chlorine minus. Minus are all the bases. We will later on study that. Okay. This is conjugate base. So HCl is strong means Cl minus will be weak or even the negligible base. See, that's why negligible. Now let's see here. So HNO3. HNO3 is the strong acid. NO3 minus is the conjugate base is very, very weak. Similarly, HF, weak. Okay. This is a weak, and you can say this is about stronger. This is also weak, but you see, this is negligible, but this S minus 2 is stronger. So that's why the stronger the acid is, the weaker is the conjugate base. Weaker is the conjugate base. Now again, so we have so far we have known what are the strong acid, strong base, what are the Arrhenius acid, Arrhenius base. Now let's discuss about the further about the ionization constant, or this is also said to be the dissociation constant. Now let's see what are the ionization constant of acid and base. Okay. So ionization constant of, so look at that. Ha is acid, right? And let's say equilibrium symbol, then H plus A minus. So ionization constant Ka is equals to product divided by reactant, right? What is the product here? Concentration of H plus, square bracket means concentration. Concentration of A minus divided by concentration of the acid, Ha. This is the acid dissociation constant. If this is strong acid, that is always greater than 1. If this is a weak acid, that is always smaller than 1. That's a very good definition, right? The good definition, what is the strong acid? Is the acid dissociation constant is greater than 1. That's the strong acid. So if the acid dissociation constant is less than 1, that is a weak acid. Similarly, the base also has a base dissociation constant. For example, MOH is the base. That will give you M plus OH minus, right? Kb, base dissociation constant, is equals to concentration of M plus concentration of OH minus. M plus means Ne, okay? That's the base. Is a sodium hydroxide, this is Na. So for example, sodium hydroxide. This is Na plus OH minus, right? This Na plus is M plus, okay? Why? Concentration of MOH. If this is less than 1, weak base. If this is greater than 1, weak, strong base. Okay, same as like that. So, a base M is stronger than other base. Now, how do we compare two bases or two acids? For example, there is one acid A. Acid A, its Ka is 5. Other acid B, its Ka is 7. So whose Ka is larger, that is more stronger, right? So A is stronger than, acid A is stronger than B if Ka is greater than Kb. Similarly, base also. If Ka, for example, there are two bases, and then Kb is greater than, for example, Kb of A is greater than Kb of B, then the base is stronger. Base. So for example, base M1, and there is another base M2, and it's a Km1. I will write that. Okay, Kbm1, K base dissociation constant of M1, and its base dissociation constant is Kbm2. So if Kbm1 is greater than Kbm2, then then M1 is stronger than M2. Done. So that's why you can compare two acid and two base, which is stronger. So acid has the acid dissociation constant, base has base dissociation constant. So that's all about the Arrhenius acid base. Okay, Arrhenius acid base. You have to, you should know, you should have water. You have to, if they are dissociated in water and they give hydrogen, that's acid. If that gives the OH hydroxide ion, that is the base according to the Arrhenius. Now second, because Arrhenius, you need water. Only it talks about the something in aqueous medium, but the reactions are not always aqueous medium, right? So that's why there is another definition. So not all of the acid and the bases are covered by the Arrhenius. That's why the Bronsted-Lowry, those scientists give the new definition. So what they say? Acid is proton accept donor. Proton means H plus donor. Okay, acid is that. Base will be a proton or H plus acceptor. Okay, it means that which can give you the proton, that is acid, which can accept the proton, that is base. Now let's go base first. For example, chlorine is the minus. If that is the minus charge, then it can easily accept the plus charge, right? H plus. Okay, it means that chlorine minus is base because it can accept the proton. Okay, so and which can donate the proton, for example, HCl. Yes, it can give you the H plus, that's why it is acid. Which can accept the proton, that is the base. Which can donate the proton, that is the acid. So that's why acid base reaction is also said to be the proton transfer reaction. That's the reason this is said to be proton transfer reaction. Okay. So, and the other thing is conjugate acid base pair. Now let's think about the conjugate acid base pair. Any pair of molecular ion that can be interconverted by transfer of a proton. That's the conjugate acid base pair. Okay. So, and the Bronsted-Lowry definition do not require the water. And now let's first of all think about the conjugate acid base pair. Okay. Let's say CS3 COOH. This is the acid. Okay. Plus NH3 gives you CS3 COO minus plus NH4 plus. Okay. So now let's see that here. This is acid minus our base, right? So its the conjugate is that. You see, its the conjugate is this. If this is acid, this is base. That's why these two are conjugate acid base pair. On acid and its the conjugate base. That pair. And NH3, NH4. NH4, look at that here. NH4 plus it is. That's why this is the base. NH3 is accepting the H plus and becoming NH4. That's why this is the base and this is the conjugate acid. So that's why acid has conjugate base and the base has conjugate acid. So the easy way, if you recognize the acid, if you remove H plus from acid, okay, what remaining is conjugate base of that acid. Now let me show you here. HCl, remove the hydrogen, what becomes? Cl minus. Okay, H is acid, Cl minus is base. Conjugate base of hydrochloric acid means that it can compensate. It is a part of this acid. So this is made up of acid and the conjugate base. So if you remember, now let's say H2SO4. This we can say H plus plus HSO4 minus. So now this is the acid and this could be conjugate base of which acid? H2SO4 acid. Okay, conjugate base of the parent acid. For example, let's say HNO3. This is the acid, and let's throw out the hydrogen, and you will have NO3 minus. So this is acid, this is parent, and this is the conjugate base of HNO3. So conjugate acid base pair is HNO3 and NO3 minus. These are the pair. Okay, so that is the conjugate acid base pair. So the easiest way to know what is the conjugate acid base pair, you just throw the hydrogen, what remaining is conjugate acid. You add the hydrogen, what becomes the conjugate acid of a base. For example, let's say NH3 is the base, right? You add the hydrogen and it will become what? NH4 plus. Okay, this is base and this is the conjugate acid. Done? So now similarly NaOH, just to throw out the OH, and what remaining is that is Na plus, that is the conjugate acid of the NaOH. So like that. So now let's see here, Bronsted-Lowry acid base definition is based upon that's why it is based upon proton transfer, right? It's based upon the proton transfer, and that reaction is the proton transfer reaction. Okay, so now let's see, these are the example of acids. Okay, these are the example of acids: Hi, HCl, H2S. These all are the Bronsted-Lowry acids. But look at that here. So now there are different other types. Look at that: H2SO4 acid, H3O plus is acid, but SO4 is minus, that is also acid. Okay, now because whatever can donate the hydrogen, that is the acid. Okay, this can donate this hydrogen. Okay, HSO4 minus. So this has both property. It can accept the H plus because it has minus. It can donate the hydrogen because it has hydrogen. That's why it can give you H plus SO4 2 minus it become, right? So, and on the other hand, it can accept the hydrogen also, minus plus H plus, and it can become H2 SO4, right? That's why this has both properties. It can accept the hydrogen, it can donate the hydrogen. That's why it can donate the hydrogen, that's why it is acid. It can accept the hydrogen, that's why it is base. Okay, so these all are acid also. However, they are negatively charged, but they are acid too. Okay, so similarly, base example, look at that here. These all minus charge are base. So, but the simultaneously HClO4, HPO4 2 minus, they are acid also, base also. Okay. So now an acid can positively charge, neutral or negatively charge. So look at that, acid can positively charge also, H3O plus positively charge, neutral H2S neutral also, or negatively charge also. For example, H3O plus positive, this is neutral and this is negative. A base can negatively charge or neutral. It cannot be positively charged, right? But it is a neutral or negatively charged. You see, OH minus, Cl minus, NH3, they are neutral, also negatively charged also. An acid classified as monoprotic, diprotic or triprotic depend upon the number of protons each may give. Of examples are this. Okay, so acid can be defined as the monoprotic, diprotic, triprotic. What does that mean? The monoprotic means if that can give only one proton. For example, HCl, right? HCl will give you H plus plus Cl minus, done. Only one proton can give. Diprotic means it can give the two protons. For example, H2SO4. Then it can give what? First of all, H plus plus HSO4 minus, SO4 minus, and a second step it again gives the H plus this, okay, H2SO4. That becomes H plus plus HSO4 minus. And this HSO4 minus can give you again H plus and SO4 minus. Now let's write that. These two cancels. That's why H2SO4 can give you how many hydrogens? 2 hydrogens plus SO4 minus. However, these two you don't get 2 at once. First of all, 1 hydrogen plus, and then next time second hydrogen plus it gives. But this is a diprotic because it gives you 2 hydrogen plus 2 protons. That's why it is a diprotic. Triprotic means it can give 3. For example, S3PO4. That will give first S plus plus S2PO4 minus. Then S2PO4 minus can give you H plus and HPO4 minus, 2 minus. And this has also hydrogen. That's why HPO4 2 minus can give you H plus plus PO4 3 minus. Now if you combine them, HPO4, this cancels. That's why H3PO4 can give you 3 proton plus PO4 3 minus. That's why it is a triprotic. It can give you 3 protons. So okay. So some acids are base also. They can be base also. They can be acid also. So for example, HSO4 minus. It has a minus charge. That's why it is a base. It can give you hydrogen. That's why it is acid. It is both. Okay, for example, H2O also. H2O can be base also, H2O can be acid also. Water can give you H3O plus plus OH minus, base. It can accept the hydrogen, H2O plus H plus, it becomes H3O plus. That's why, right, it can accept the hydrogen. And it can give you the hydrogen, that's why both. That's why it is acid and base both. So now, HClO3 minus ion, for example, can give up a proton to become CO3 minus, or it can accept a proton S2CO3. A substance that can act as either acid or base is said to be amphiprotic. So we discussed that HSO4 minus, right? This is base also because it is minus, negatively charged, and it can accept H plus. That's why it is base. And it can give you hydrogen, H plus plus SO4 2 minus. That's why it can give you hydrogen. That's why it is acid. It can accept hydrogen. That's why it is base. So a substance which is either acid or base both, it is the amphiprotic. Amphiprotic means it is acid also, it is base also, both. This is amphiprotic. Okay. So H2O is also amphiprotic because H2O can accept hydrogen and it becomes what? H3O plus. That's why it accepts hydrogen. That's why it is base. And it can give you hydrogen. For example, H2O plus can give you H plus plus OH minus. That's why it is acid. It is both. That's why so this the water is also amphiprotic. That is because it is acid also, base also. So a substance cannot be Bronsted-Lowry acid unless it contains the hydrogen atom, but not all hydrogen atoms in most compounds can give up. For example, acetic acid, these are okay. There is an inverse relation between the strength of acid and the strength of its conjugate base. We have already discussed the conjugate acid and base, right? If acid remove the hydrogen, what remains? That is conjugate base. So they have the opposite relation. If acid is strong, its conjugate base is weak. If acid is weak, its conjugate base is strong. For example, let's say HCl is strong, but what is the conjugate? HCl is acid. its conjugate base is what? Cl minus, just remove. So it is strong acid. This is the base because it is minus charge. That's why it is a weak base. So, right, and that's the weak base. Okay. So now, yeah, we have this about the water, right? So water is a Bronsted Lowry and base, Lowry acid and base. We already have said that. Okay. So water is the it donates, right? So okay, we already discussed this. Okay, water is, it donates. Look at that. HCl is this, H2O it accepts. So water is the base and HCl is acid. So in case of the HCl and water reaction, let's see that HCl and water reaction. So let me see that here. Let me remove that arrow here, right? HCl and H2O. HCl plus H2O. So what is this? Becomes H3O plus Cl minus, right? So look at that, which is accepting the H plus. This water is accepting H plus, right? So that's why what? Accept the proton, that is base. That's why it is base, right? In another case, let's see that NH3 plus H2O, then it becomes what? NH3, NH4 plus OH minus, right? What is this doing? This is losing H plus, or it is donating H plus. That's why this is acid in this case. Okay, that's why water is both. So water is amphiprotic. It can act as either base and acid, H plus ion. There are other also amphiprotic. For example, H2PO4, HSO4 minus, HCO3 minus, H2O, etc. Okay, that's it for today. Thank you so much, and we will go further in this acid-base equilibria. And this I would like to stop this video right now, and we will go further to the next day's material. And thank you so much for right now. And if you have any question, ask me or email me. Okay, thanks.